Good day, learner. My name is Dr. P.I. Ogunyenka. I will be taking you on Star 202, Inferential Statistics. I'll be working along with Professor D.A. Agumbiade to facilitate this class. You recall in the last class, Professor Agumbiade introduced this course to you and took you on the topics, sampling theory and estimation techniques. Today, in this session, I will be putting you through on simple correlation analysis. At the end of this session, you will be able to understand what simple correlation analysis is all about. You'll be able to apply the two types of simple correlation analysis which will be considered in this course. These two types include Pearson's product moment correlation coefficient and Spearman's rank correlation coefficient. You'll be able to look at how to break ties in the rankings which is involved in Spearman's rank correlation coefficient, and you will be able to apply correlation coefficients to everyday life. Correlation coefficient is what we apply in everyday activity. Let us take instance of the conventional markets. When there is increase in price of products in the market, then the consumer will prefer to reduce the amount demanded. However, when there is increase in the price of products in the market, the supplier or producer will prefer to supply more of the quantity, increase the quantity supplied into the market. Here we are talking about the relationship between quantity of products supplied to the market with the price. Again, we have also considered the relationship between the quantity of product demanded by the consumer and the price of the product. This is a very good example of correlation. Correlation is a degree of association between two or more products. In this case, in this session, we'll be considering two products or two variables. So the degree of association between two variables talks about correlation. The degree of association could be positive or negative. It could be high or low. So correlation coefficient or coefficient of correlation is represented by R, and it measures the strength of linear relationship between two variables in this case. Let us look at the graph to explain what we mean by positive correlation and negative correlation, and even what we call no correlation. We shall be having a perfect and positive correlation if the value of R is representing correlation. Yeah, if the value of R is 1, then we say we have a perfect and positive correlation coefficient. That value 1 is the coefficient, the numerical representation of the correlation. However, if we have the value of R to be -1, then we say we have a perfect and negative correlation coefficient. If the value of R is 0, then we say there exists no correlation between the two variables under consideration. There could be the case where the value of R is not negative, it's rather less than 0. Then we say we have what we call negative correlation coefficient. Finally, if the value of R is not 0, but it is greater than 0, then we say we have positive correlation coefficient. The first graph here explains the when we have positive correlation coefficient, that is, the value of the linear graph increases, then we have positive correlation here. In the second graph, there exists no correlation because the value of r is 0. And finally, in the third graph, here we have the negative correlation because the linear relationship declines, goes down. Here we have negative correlation. There are two types of correlation coefficients, two types of correlation that will be considered in this session. 1. We shall be considering Pearson's product moment correlation coefficient. 2. We shall be considering the Spearman's rank correlation coefficient. These two types of correlation, they are formulas, two formulas that we use to compute the correlation coefficient based on conditions. The condition is this: when the data you are given, when this data, or you call it distribution, violates the normality assumption, then you make use of Spearman's rank correlation coefficients. On the other hand, if normality assumption is obeyed by the distribution or the data that you are, set of data you are given, then you make use of Pearson's product moment correlation method. We shall pick this method one after the other. First, let's look at Pearson's product moment correlation coefficient. I will also refer to it as Pearson's product moment correlation coefficient. The formula for Pearson's product moment correlation coefficient is presented in the first equation here as R measuring the relationship correlation between y and x variables equals to the numerator here. This numerator, remember I said we are measuring correlation between two variables in this session. Those variables are represented with x and y. So at the numerator of the right hand side of this equation talks about the summation of the product of x and y minus bracket open summation of x multiplied by summation of y divided by the sample size represented by n. Small letter n represents the sample size, which talks about the number of observations in the data set you have. The denominator of the right hand side of this equation talks about the square root of the product of summation of the square of x, summation of the square of x minus the division of the square of the sum of x divided by the sample size n. This is multiplied by the summation of the square of y minus the division of the square of summation of y divided by the sample size n. Or this denominator is under the umbrella of the square root. By further simplification of this first equation will lead to this second equation. However, the condition is that r, the value of r, that is the correlation coefficient, will lie and must lie between -1 and 1 inclusively. And it is the value of r that you get that we shall then interpret as I've rightly mentioned earlier. Let us pick an instance and to the application of Pearson's product moment correlation coefficients. This here we have the distribution or the data set of Nigerian government income represented by X and Nigerian government expenditure represented by Y for 12 months. we are expected to calculate this income, which is measured in millions of naira. We are expected to calculate the Pearson's product moment correlation coefficient. To calculate the Pearson's product moment correlation coefficient, we have to introduce some new columns to compute some estimators that will be needed for the computation of Spearman's rank, computation of Pearson's product moment correlation coefficients. We have been given the value of X for the 12 months, and we have been given the value of Y for the 12 months. Remember that X represents the Nigerian government income and Y represents Nigerian government expenditure. We are expected to obtain the X square. This is the square of X, which is the fourth column 1, 2, 3, and 4. So this fourth column here is talking about the square of the value of X for this 12 months. This is the square of the value of Y, and this is the product of X, of the value of X and Y for the 12 months. The square of 11.50, which is the first observation in X, 11.50. The square of 11.50 gives 132.25, and you do this for the 12 months. Similarly, for the value of Y, the first observation is 11.25. The square of 11.25 gives 126.56, and this is done for the 12 months. For the last row here, we obtain the total of the X for the 12 months. This is the total. The total of X for the 12 months gives 137.25, and the total of Y for the 12 months gives 138.25. This is the total of the X square for the 12 months, and this is the total of Y square for the 12 months. Finally, this is the total of the product of X and Y for the 12 months, which is 1,599.13. We move ahead to substitute these summations that we have obtained in the previous table into the formula of Pearson's product moment correlation coefficient. Once, if you substitute for the summation of the product of S square, which has been obtained in the previous table, which you obtain here to be 1,608.12, minus this, the summation of X is obtained here, times the summation of Y divided by small letter n, which is the total number of observations, which is 12 in this case. Similarly, you substitute into the denominator as well to obtain this. By further simplification, you obtain R to be equal to 0.75 to 0.70 to 2 decimal places. One thing you observe about the R here is the correlation coefficient for Pearson's product moment correlation. And one thing you observe, two things you observe about the value of R here. You realize that the value is positive and the value is high. 0.7 is close to +1. So this will then be interpreted that there is 70% positive and high correlation or relationship between Nigerian government expenditure and Nigerian government income within the 12 months under consideration. Let us take another example. Here we have the value of 10 years for Nigerian government income and inflation and gross domestic product (GDP) for 10 years. The question is, we are expected to calculate the Pearson's product moment correlation coefficients for government income and inflation (Y) and X. So government income has been represented with the variable Y, while government inflation, the inflation rather, has been represented with X here. The GDP, gross domestic product, has been represented with Z. Placing special attention on Y and X to compute for the Pearson's product moment correlation coefficients. We need to obtain new rows here to obtain the product of X and Y, the product of Y and Z, the product of X and Z, and the total is presented in the last column here, titled as sum. So we then move ahead to substitute this summation into the formula of Pearson's product moment correlation coefficient. Again, we substitute into the formula here. If you substitute these values, which have been obtained in the previous slide, into this formula of Pearson's product moment correlation coefficient and simplify further, then you will obtain this value for R. So here the correlation coefficient is 0.9620, which is 96%. 96%. The interpretation attached to this is that, one, you will observe that the value of 0.9620 is positive and it is high. High in the sense that it is close to plus 1. So here we conclude that there is positively high correlation coefficient of 96% between the government income and inflation for the 10 years under consideration. There is 96% correlation coefficient between the government income and inflation for the 10 years under consideration. Next, we go to the computation and application of Spearman's rank correlation coefficient. As earlier mentioned, the condition for the use of Spearman's rank correlation coefficient is that there must be violation of normality assumption by the distribution or the data set under consideration. The formula for the computation of the Spearman rank correlation coefficient is presented as capital letter R equals to 1 minus the fraction of 6 multiplied by the summation of the square of the difference between the rank of the two variables under consideration divided by the product of n and n squared minus 1. At the numerator here, D here represents the difference between the rank of the two variables under consideration. We shall see the application of Spearman's rank correlation coefficient as we move ahead. Again, just like Pearson's product moment correlation coefficient, the value of Spearman's rank correlation coefficient must lie between -1 and 1 inclusively, and it follows the same interpretation just like the Pearson's product moment correlation coefficient. Let us take an example on the application of Spearman's rank correlation coefficient. Here we have these 6 observations of two variables, X and Y, where X is the income of a company and Y is the expenditure of the same company. We are expected to compute the Spearman's rank correlation coefficient of this dataset or distribution. We have been given X as a variable and Y as variable. So we are representing placing them on 2 columns here. On X here, we are to rank the value of X here. Going by the ranking of value of X, the ranking of value of X is presented in 3rd column here as capital letter R subscript X. Let us see how this ranking goes. The least value of X here is 16. This 16 is given the rank 1. The next value to 16 is 19 and is given the rank value of 2. The next value to 19 is 22 and this is given the rank value of 3. The next value to 22 is 24 and this is given the rank value of 4. The next value to 24 is 25 and this is given the rank value of 5. Finally, the last value, which is the sixth value in X, is 28 and this is given the rank value of 6. This is how the rank value for X is gotten, which is presented in the third column. The fourth column presents the ranking of the values of Y. Here, the ranking follows the same method, just the way we did for the ranking of X values. The fifth column here, which is represented with D, equals to the difference between the ranking of X and Y. The difference between the first observation, which is the difference between 3 and 6, will be minus 3. So also 4 minus 3 for the second observation is 1. Next observation says 5 minus 2 is 3. Next observation says 1 minus 1 is 0. Next is the difference between 6 and 5, which is 1. Finally, the difference between 2 and 4, which is minus 2. The last column here, we obtain the square of the difference which was obtained in the previous column. The square of minus 3 is 9. The square of 1 is 1. And this is obtained for the last observation, which is the square of minus 2, which is 4. We then obtain the summation of this square to be 24. Finally, we go ahead to substitute into the formula of Spearman's rank correlation coefficient, which is 1 R, capital letter R, equals to 1 minus 6. Summation of the subscript I square has been obtained as 24. Here, you substitute for this summation to be 24, which is what we have here. And at the denominator, you have small letter n, which is 6. We have 6 observations, 6. And here we have n square, which is 6 square, which equals to 36 minus 1. When you simplify this further, this will give R equals to 0.3143. So the value of R here is approximately 0.31 to 2 decimal places, which is 31%. And two things you observe about this value. 1, it is positive. 2, the value is close to 0. So here we have positive and low correlation coefficient between the income and expenditure of the company. That is the interpretation attached to Spearman rank correlation coefficient. However, in Spearman's rank correlation coefficient, there could be instances where there will be tier of ranks, where you have 2 observations having the same rank. And so what you do in such case, you have to find the average of such rank, or of the 2 ranks. So let us look at an application of the tier of ranks in Spearman's rank correlation coefficient. Picking an instance, this we have the data of the money deposited in 2 commercial banks for a year, or rather yearly deposit of money into two commercial banks. This is measured in billions. We are expected to calculate the Spearman's rank correlation coefficient of this data set. So for the first bank, the money deposited is represented with X, and for the second bank, the money deposited is represented with Y. The values are given here. Now we need to compute the ranking of these two variables. So for X, the least value in X is 63, and this is given the rank value of 1. Next is 64. It is given the rank value of 2. Next is 65. It is given the rank value of 3. Next is 66, which is given the rank value of 4. Next is 67, which is given the rank value of 5. Next is 68, which is given the rank value of 6. However, you observe that there are two 68 values. This is 168 here, and this is another 68 here, meaning that 168 will be what? Will be 6 by ranking, and the other one will be 7 by ranking of the same values or observation, 68. So this is an example of tie and rank. So what do we do in this case? We take the two ranks, 6 and 7. You add it together, which will give us 13. Divide it by 2, which will give us 6.5. So the rank for each of these 268 values will then be 6.5 and 6.5. With this, we have covered the ranking value for 6th and the 7th. Next, we move to the 8th item. The 8th item is 69. Again, there are two values of 69. 69 here, 69 here. Again, we are observing ties of rank. So what we do is we have 68 here. We have 68, or rather, we have 69 here. We have 69 here. We also have 69 here, with the ranking of 8th and 9th. So we find the average of 8th and 9th, and that will be 8 plus 9, which gives 8 plus 9, which gives 17. Divide it by 2 to obtain the average of this ranking, and this will give us 8.5, which means the rank value for 69 and 69 that we have here will then be 8.5 each. Next, which means for this, we have covered for the position of the 8th value and the 9th value. Then we move to the 10th value. So the next value after 69 is then 70. So 70 then takes the 10th rank. Next, we have 71 taking the 11th rank. Next, we have 72 taking the 12th rank. And this is how the ranking for X goes, where we have ties of a rank. So also we have similar ranking for the values of Y. The next column, which is the 5th column here, we have the difference between rank of X and rank of Y. And this gives 4 minus 7.5 gives minus 3.5. Here we have 2 minus 3.5 gives 1.5 up to the last observation. And the last column here, we obtain the square of the difference of the rank which was obtained in the previous column to be this. And finally, we find the total or summation of the square of these difference to be 72.50. Substituting these values into the formula of Spearman's rank correlation coefficient is done on this slide, and here we obtain, after simplification, R to be equal to 0.7465, which is approximately 75%. Two things you observe about this, the value of R here. One, the value of R is positive, and two, the value of R is high. 0.75 is close to 0.1. And so we conclude that there is a 75% positive and high correlation between the money deposited in the two commercial banks. With this, we have completed the content for this session. A quick revision or summary of what we have done. We have been able to look at what is correlation coefficient, which is the measure of association between two variables as covered in this session. The value of correlation is called correlation coefficient, and the correlation coefficient could be positive or negative. The value of correlation coefficient lies between +1 and 1 inclusively. It is 1 plus 1 when it is perfect and positive correlation coefficient. It is -1 when it is perfect and negative correlation coefficient. It is 0 when there is no correlation at all, and it is greater than 0 when there is positive correlation. It is less than 0 when there is negative correlation. We talked about two types of correlation coefficients for this session, which are Pearson's product moment correlation coefficient and Spearman's rank correlation coefficient. We also mentioned the conditions for the use of the two, which is the violation or satisfaction of normality assumption by the dataset or distribution under consideration. I also mentioned the formula for the calculation of Pearson's product moment correlation coefficient and the formula for the computation of Spearman's rank correlation coefficients. For your assessment, you can lay your hands on the exercise given on the slide to compute for Pearson's product moment correlation coefficient and also to compute for the Spearman's rank correlation coefficient. Lay your hands on this exercise. Increase your competency in handling correlation coefficients. Thank you for listening.